Thank you very much. So, my name is Sabrina Maniscalco. I'm an Italian living in Finland, and I have the honor today to tell you something about open quantum system and simulations in open quantum systems. And because the audience is so diverse, I think I will give a very general lecture. So what I will do is mainly highlighting. I will begin by highlighting what I think are the reasons why we study open quantum systems. And then I will introduce some formalism and give some basic ideas of what the main problems, open problems are. And obviously I will make a choice. I will select some possible open questions. But the main idea really would be to try to give you a general framework and a reason why we are studying open quantum systems and the simulations of open quantum systems. So I begin with the why. And to define the why and to clarify what we mean with reasons for studying open quantum systems, I have to say first what open quantum systems are. And this is quite simple. Open quantum systems are basically quantum systems interacting with their environment. The environment can be a environment or also classical noise. Generally, we consider the effect of noise on quantum system. And generally, quantum environments can be bosonic or fermionic of nature, but the main idea is that what we identify as the system or the open system is what we are interested in, what we want to measure, for example. However, the evolution of this quantum system is also subjected to the effect of environment, which is inevitable, okay? So the environment generally contains very many degrees of freedom, infinite, in the case of an infinite environment or reservoir or a thermal bath. And however, we don't want to follow the evolution of the degrees of freedom of the environment, but we want to see what are the effects of the presence of the environment on the system, on the open system. So this is the general framework. And the reasons why we want to study open quantum systems are, well, the first one you may say, well, this is trivial, but let's say it, is because all quantum systems are open. Okay. Schrödinger equation is an equation of motion for a closed quantum system. It's just an approximation that does not describe reality as we see it in experiments. There is no way there are certainly approximations, and we are nowadays in our field, for example, in a situation in which many experimental scenarios are so developed that we are able to isolate very well quantum system from noise. So we can describe a number of phenomena that are important, for example, for quantum technologies, because experiments are so precise and so advanced. But in any case, there is no way to avoid noise. So the proper way of describing quantum physics is through open quantum system formally. Okay? Of course, the second motivation that I would like to give is a foundational type of motivation. So open quantum system theory is the framework where we can assess and describe really basic open problems in quantum theory, such as, for example, the measurement problem, or also the quantum to classical transition. Okay? So there are a number, these are just examples, there are a number of foundational issues which find their proper description in terms of open quantum system theory. So by introducing the effect of the environment, decoherence induced by the environment, and by formalizing, and indeed experiments have shown things like, or very fundamental properties such as Schrödinger cut decoherence, and many of what were in the past only Gedanken experiments. Okay? There is also there are a plethora of other foundational issues, but I will just mention these as an example. Of course, the third and important reasons is related to quantum technologies. You probably, maybe not all of you, have heard that decoherence is the enemy of quantum technologies. What does it mean? Quantum technologies are a number of technological applications of quantum theory, mostly exploiting some peculiar features like quantum entanglement, that are applied to sensing and metrology, computation, communication, simulation, and so on and so forth. And they rely on specific quantum effects, like entanglement, as I said. Entanglement is a resource for a number of these quantum technologies. However, it is known, and it has been shown also experimentally, that these quantum features are very sensitive to the effect of noise, and therefore they are quickly destroyed. And as a consequence of this, there is a limit lifetime of any quantum device or quantum technology due to noise. Okay? So how can we proceed? Obviously, one of the ways is to model environments in order to study their effects on the open system, performing, for example, the quantum computation, and model it allows us to understand it in order to counter it, to minimize it, to find ways of dealing with the presence of these environments. So for all quantum technologies, the understanding of open quantum systems dynamics is crucial. It tells us how to enhance the lifetime of quantum devices. Okay? And obviously, since it isn't easy in general to describe, as we will see, open quantum system dynamics, this requires a number of approximations that we will describe in the following. But now the fourth point is a little bit, I'm not saying contradicting, but it's a new take on the idea that decoherence is an enemy. I'm talking about quantum reservoir engineering. And control. So, for a very long time in our community, there was this idea that we needed to minimize the effects of the environments and the coherence in use of the environment because this was limiting the operation time of any quantum device. However, it turns out that even if the environment is inevitably present, you can somehow think of modifying it in order to either enhance coherence or also even to engineer types of decoherence that allow you, for example, to have as final states of the dynamics specific entangled states, which are resources for quantum computations. So quantum reservoir engineering somehow changes the idea that the environment is the enemy, and instead present us with a scenario in which we can act in two possible ways. One is modifying some of the parameters of the environment, for example, the spectral density, in order to somehow make it better for the specific quantum technological purpose that we have in mind. And the second important idea is that when the environment, when the system is sufficiently isolated from the environment, we can still actually add some dissipative sources, some environment prepared at hand, and these may allow us to reach certain entangled states or certain target states that are useful as resource for quantum technologies. This has been proposed and realized even experimentally. For example, there are very famous experiments in trapped ion context, but not only, in which reservoir engineering has been proven, and in fact, Bell states, certain entangled state has been realized in this way. And of course, there is clearly also, in this scenario, the issue of quantum optimal control and of quantum control in general in the presence of open systems. So there are certain techniques and technologies and certain ideas of what we can do other than just reducing the effects of the environment in order to improve quantum technologies. And of course, another point that somehow is important in this framework, especially to stress, is quantum simulations. Now, here again, we have two possible scenarios. One is a scenario in which we want to consider the effects of noise on quantum simulations of other systems, of certain systems of interest. But the second one is a scenario in which we want to simulate open quantum systems. So we can use a certain quantum system to simulate open quantum system controllably. And this allows us to address problems that are open in the theory of open quantum systems. One example of an open problem of theoretical interest in open quantum system theory is, as we will say it, I will say it in a moment, the general form of the equation of motion for the dynamics of an open system. So there is at the moment no known solution to this question. We do not know in the most general case what is the most general form of equation of motion, the analog of the Schrödinger equation, if you want, for an open quantum system. We know it only for very specific cases. So this is a foundational problem that can be addressed in this framework. And another point is quantum probing. Luckily, this is the last one. It looks nice like this. So quantum probing. Or the last one that I want to make for now. So quantum probing is a scenario in which we use controllably a small quantum system. It could be an atom confined in a certain optical potential. And we let this atom, that I will call the probe or the open system, interact for a certain amount of time with a many-body complex system. It could be a complex network or a many-body system, optical lattices, cold atoms in optical lattices. Many examples can be considered. And through that, what is our aim? Our aim is to understand the properties of the many-body complex system by probing with another small single atom, for example. And we assume that we can control the interaction between the single probe and the environment perfectly. So we know how to immerse it in the complex system, how to turn on the interaction and how to turn it on, off, and also we can change the interaction strength. So this small probe is now our open system, and the many-body complex system is what we want to study, okay? And the framework is an open system framework because the many-body system is inducing decoherent dynamics into the probe. So one idea might be to try to map properties of the many-body complex system into the decoherent dynamics of the probe. The many-body complex system can be a system undergoing a quantum phase transition. For example, in the Bose-Hubbard model, a transition from superfluid to Mott insulator regime. And so this is obviously a global properties of the many-body system. But by immersing the probe, we want to see if this global property, that could be the quantum phase of the ground state of the many-body system, can be detected in the type of induced decoherence on the probe. This can be done with complex many-body system, but it can be also something that we started to explore, for example, with complex quantum networks. Complex quantum networks can be environments of probes that induce certain decoherence in the probe, and you may try to think which properties of the complex quantum network you can detect through the probe dynamics. It could be, for example, the connectivity of the network, or it could be certain properties related to the topology of the network. There are several obviously possibilities, okay? Because depending on these properties, the induced dynamics of the probe will change, and then you can measure the probe. The probe is always what you can measure, obviously, and detect properties. Okay, now this is my first part of motivation, but at this point I would like to ask at least those of you of the Open Quantum System program, am I missing something? Do you want to suggest some other motivations? I try to keep them very general, so many things go inside these chapters, but please, if you want to at this point suggest and contribute to the lecture by suggesting something, please, it's your moment. No? Really not? Okay. Very good. I live in Finland, so I'm used to people not answering questions. All the time. As an Italian, it's a little bit, but I have a lot of training in this. Okay. Okay, now, second part, after the motivation, let's try to describe a little bit the mathematical formalism for open quantum systems. How do we describe open quantum systems? And obviously, the main idea, or what has been used in a long time in our community, is through equations of motion. So we try to define a certain equation of motion that describe the dynamics of the open system. Clearly, I'm thinking in terms of description of the quantum states in terms of a density operator that I will call rho s. This is a positive define and trace one operator. And generally, we can consider both continuous variable and discrete variable systems. But most of the things I will say are valid for both. So rho s is my density operator of the system. What has been the most famous, I say probably is the king result of open quantum system theory, the most famous equation of motion for the density operator of the system is known as the master equation. And specifically, the one that has been used the most in the field is the so-called, I call it GKSL master equation. Why? Well, generally this is known as the Lindblad master equation, but the GKSL stands for the fact that also Gorini, Kosakowski, and Sudarshan, the same year as Lindblad, obtained the same result. Okay, and this is the form of the equation of motion. Right? I will always consider h bar equal to 1 units of h bar in the following. Rho dot s of t minus I commutator in the Hamiltonian of the system. Rho s of t. This first part describes the sort of unitary dynamics of the system. And then we have the dissipative part that is related to the interaction, or more properly related to the interaction with the environment, which has the following form. We have LK dagger minus 1/2 and yes, this is the anti-commutator part. So these coefficients here are positive or non-negative decay rates. They describe the decay of the quantum system induced by or caused by the interaction with the environment. And these are operators. I apologize, I will not use the hat for simplicity and for quickness. I will not use the hat for the operators. This is the Hamiltonian of the system, and these are operators, the Lindblad operators, that are describing the dissipation in each individual dissipation channel due to the interaction with the environment. One of the examples that generally in quantum optics is considered and done and studied extensively is the case of a two-level atom, ground and excited state of the atom, interacting with the vacuum of the electromagnetic field, and therefore there is only one decay channel. Gamma would be the decay rate of the decay channel, and so in this case, I have only one K, and the decay rate, so Lk, is just sigma minus. Okay, the Lindblad operator there is only one, and is sigma minus, and this basically describes spontaneous emission. If the two-level atom interacts with a T temperature environment, I have two Lindblad operators or jump operators, sigma minus and sigma plus. Of course, sigma minus is So clearly, there are a number of equations of motions that are described within this formalism. However, this formalism isn't general. Okay? This formalism, this master equation, this equation of motion, is a consequence of a number of approximations. The most famous are weak coupling between system and environment, and also very shortly living correlations between system and environment, the Born-Markov approximations. And this can be derived microscopically from an exact approach. However, it is not the most general form of equation of motion. And in particular, there are certain scenarios, especially when one considers reservoir engineering and a variety of quantum technologies, for example, in solid-state systems where the noise is so-called strongly non-Markovian noise, we will describe it in a moment. There are a number of scenarios where this equation of motion does not describe the dynamics of the system, and we need to go beyond.
What is the environment for this two-state system?
Sorry? Which type of...
What is the environment? You speak of the environment.
Yes.
It's only
Very good point.
two states.
No, here, this is the system. This is my description of the system, and this rho S is the density operator of the system. The environment is the vacuum of the electromagnetic field, and the master equation is always an equation of motion for the system only. So the effects, all the information on the environment are here in the decay rates, and also in the form of this dissipator part. So the information which contains the density of modes of the environment and everything, they are related, they are contained into these decay rates, and they are somehow shaping the form of this equation.
In cases like this, you can derive this, right? You can start from the quantum description
this is exactly,
and derive,
precisely. This is exactly what I'm going to say now. This is my next point. So what do we do in general? One of the best ways or proper ways of describing open quantum system, when you can do it, like in this case, for example, is a standard example, is to consider the total, what I call the microscopic derivation of the master equation. So what you have in this case is a total Hamiltonian for system plus environment. We go to your description of the environment here. And the total Hamiltonian, remember, this is a bipartite system. So the total state will live in the tensor product of the Hilbert spaces of the system and environment. And the Hamiltonian for the total system generally has the form Hamiltonian of the system, identity of the environment, plus identity of the environment, Hamiltonian of Hamiltonian of the system, Hamiltonian of the environment, plus an interaction term, which, for example, can be quite generally expressed in this form. GK are some coupling constant. This goes from 1 to, well, never mind, the sum over several operators. And then I have SK tensor product EK, where these SKs are operator of the system and EKs are operator of the environment. They are generally Hermitian. So I have a microscopic description of system and environment, and what is next is obviously to understand how to go from here to this level. Okay? And there are a number of techniques for doing this. I would just want to point out within this framework a number of techniques and methods, for example, Nakajima-Zwanzig and projection operator techniques and time convolutionless projection operator techniques. There are several frameworks. What I want to point out is an important property that is generally not, some people forget, let's say, but it is crucial, okay? To point out this property, let me here draw an example of the evolution at the level of the total system and at the level of the reduced system, okay? So at the level of the total system, I will have initially, let's call it the initial time 0 instead of T0, if you don't mind, okay? I will have initially a density operator for the total system, and then I will have an evolution, which is, of course, unitary, because the total system is closed, okay? And from here, I clearly have rho T of T, which is UT rho T of 0, UT dagger, with UT the evolution operator for unitary. Now, if I trace here over the environment, I obtain rho S. This is the trace over the environmental degrees of freedom. I obtain the initial condition. And of course, similarly here, a trace over the environment gives me rho S of T. Okay? Now, importantly, in all the microscopic derivations, or in most of the microscopic derivations in which we obtain an equation of motion like this one, a master equation, there is a fundamental assumption, okay? And this assumption has to do with the form of the total state of system and environment at initial time. So it is assumed that at time t equals 0, I'll write it here, this is crucial.
By right this assumption, you can, in principle, you can realize any initial conditions.
In principle, you can, but if you want to write this master equation, then it's, you must. There is no way of deriving a Markovian master equation this form if you don't make a factorized initial condition assumption. It is a crucial assumption in order, clearly it is an assumption, but it is also something that it is related to, I mean, experimental is not far from what you can do, because it can be related through measure, it can be obtained through initial state preparation on the system and environment. There are a number of experimental scenarios which we work with, in quantum technology specifically, in which we can actually prepare an initial state of this form. And in this case, all this formalism and what I'm saying hold. In this phase. But this is an assumption that we need to do. And in fact, we need to do much more than this to derive this master equation. As I will say it in a moment, we need to assume for the fully Markovian Lindblad master equation that this uncorrelated initial condition, factorized initial condition, holds at all times, not just at the initial time. It's a much, much stronger assumption. Okay, but this is the minimum that we should do for any master equation. But we begin with this, and here, if I have this assumption, then I can introduce for the description of the time evolution of the reduced density operator, the open system operator, a family parameterized by time of linear maps that are completely positive and trace preserving, and this is known as the dynamical map describing the time evolution of the reduced system. For those of you with a quantum information background, completely positive and trace preserving maps are called quantum channels in quantum information theory. So the dynamical map is a family parameterized by time of quantum channels. And this fully gives me the evolution of the system, the reduced system, my open system, at all times. And obviously, well, not obviously, but worth mentioning here also that this dynamical map is something that is related to the form of the master equation, because the form of the master equation, if I write this in terms of a superoperator called the Lindbladian or the Liouvillean, the dissipator of the master equation, this superoperator L acting on the rho S of t is the generator of these dynamics, the generator of the dynamical map. So there is this connection between the two. Okay, so this is just an idea of some of the approximations or the mathematical formalism that you may use to describe master equations. There are questions about these very basic settings. At the moment, we are just establishing the basic setting. Okay. Now, the next thing that I will introduce is what if we want to go beyond? What shall we do if we want to describe dynamics in situations in which this weak coupling and Markovian approximations are not satisfied? What is the framework that we have to use? I think it's interesting to start from a classical analog of this situation. So what we are talking about here is what is known as the Markovian or non-Markovian distinctions in the dynamics of open quantum systems. So this type of equation of motion are clearly such that there is no influence on the past history of the system for the future history. So there are no so-called no-memory effects. Okay? So it's what we call the typically Markovian master equation. And obviously, one main distinction in the dynamics of open quantum system is whether or not the past or some way or some form of memory effects influence the dynamics of the open system. And how do we describe these situations? What do we need? This is important. This Markovian versus non-Markovian, or if you want, memoryless versus memory distinction is very important, again, in a variety of contexts here. And I want to point out, maybe I will do it here, why. So why the Markovian versus non-Markovian division is important in open quantum system theory and quantum simulations. Okay? What are the fields that are mostly affected by this? Some of the things are basically repetitions of what is written there, but there are some specific points. The first point is related to the fact that for quantum computation, in a number of solid-state implementations of quantum gates and quantum devices, the type of noise induced by the environment, that can be also classical, is typically non-Markovian. So we cannot apply anymore this formalism. Okay? And when this happens, error correction, or quantum error correction, strategies are very different. We need to change dramatically the way in which we think and we implement quantum error correction. So there is a need, especially now that many implementations of small quantum computers are based on superconducting qubits, for example, devices, which are solid-state devices. We need to understand better how noise works there. There's a lot of non-Markovian noise, 1/f noise, and we need to understand how to modify these protocols in the non-Markovian case. Similarly, in the case of quantum reservoir engineering, we may want to explore, for example, strong coupling scenarios, or scenarios in which we want to actually maintain the correlations between system and environment for longer. Because it may happen that these memory effects may be useful for some of the quantum technological applications. Okay? We will see that memory effects in some cases describe or imply or cause the return or some quantum feature that was previously lost because of the interaction with the environment. So, for example, you may consider the dynamics of quantum entanglement, and in the Markovian case, you just lose quantum entanglement. In the non-Markovian case, because of memory effects, you can regain it at a later time. So many somehow ideas like we have to have gates that operate as quickly as possible because we want to maintain entanglement for in the highest possible level. This becomes different when we work with non-Markovian dynamics because this entanglement can actually oscillate. So sometimes might be better to wait longer, to have a return of entanglement. So in quantum reservoir engineering is one of the other reasons. The other point is a field known as quantum biology. So a field in which people started to study effects or possible presence of quantum coherence in certain biological systems, and very often the type of environments that characterize these very complex quantum systems are in need of a non-Markovian description. And of course, there is, I would say, another interesting point is the cross-fertilization between quantum information theory and open quantum systems theory. So there are a number of concepts that are very typical of quantum information theory, like, for example, the way of quantifying information and how information is exchanged, in this case, between the open system and the environment. And there are ways of using certain concepts of quantum information theory to describe open quantum system dynamics, and specifically, for example, memory effects. So there have been attempts to quantify non-Markovianity and the presence of memory effects, more than attempts. There exist theories and also experimental demonstration of situations in which memory effects and non-Markovianity are described or are carried by information carriers. So actually they can be seen as an exchange of information between system and environment, and a partial return due to the memory of information into the system, of quantum information. And people have been using different quantifiers of quantum information and so on and so forth. So there is an interesting cross-fertilization between quantum information theory and open quantum system theory at the same time. And I think, let me see if I have some more points. And of course, everyone can still say if there are more points related to quantum non-Markovianity, or points of interest, why it is interesting to study. But I think that if I think about something else, I will add it. But I think that these were the main ones that I wanted to consider. Quantum engineering is related, of course, quantum reservoir engineering is, of course, related to quantum simulations, quantum computation, quantum biology, cross-fertilization, and obviously the fundamental aspect, which has to do with the fact that we want to understand the most general, for example, we want to understand the most general form of the equation of motion for an open quantum system. Now, in the Markovian versus non-Markovian, this is what we want to try to understand in the quantum scenario. The first thing that I would like to mention is the fact that we would be tempted. I'm just checking my time. How much time?
15.
15 minutes. Very nice. Okay. We would be clearly tempted or trying to introduce the concept of quantum non-Markovianity starting from the classical notion of Markovianity. Okay? So the concept of Markovianity for a classical stochastic process is very well defined and very well known. So we may think that there might be a way of extending this classical notion to the quantum case. And it turns out that this is unfortunately not the case, and the reason why it is impossible, really, a direct generalization of the classical idea of Markovian stochastic processes to the quantum case is a very fundamental one, which has to do with the nature of measurement processes in quantum systems. Okay, so I want to underline here what is the origin of this problem, of an extension of the concept of quantum non-Markovianity from the classical Markovianity or non-Markovianity situation. And in fact, I will not even need to consider the classical definition of a Markovian stochastic process. The problem is really even more fundamental, and it has to do with the definition of joint probability and also, therefore, of conditional probabilities in classical and quantum case. In particular, in classical case, there is no problem, but in the quantum case, as we will see, actually it is problematic to define it. So let's begin with the classical case. Okay, and in the classical case, we have a classical stochastic process. And we describe it as it takes values, discrete values. I will indicate with x tn or ti. This is the set of script with I. And we can characterize this classical stochastic properties in terms of the hierarchy, of a hierarchy of joint probability distributions. And I indicate with Pn, I have x of t n, x of t n minus 1, x tn t1, the endpoint joint probability distribution. Okay. And one of the conditions to define a proper hierarchy of joint probability distribution is the so-called Kolmogorov consistency condition, okay, which is expressed by the fact the sum over xtm of Pn xtn minus 1 gives me the Pn minus 1 x x t1. Okay, well, I'm summing over all the realization at Tn minus here. And of course, this is something which, I mean, it is needed to define a proper classical hierarchy of joint probability distribution, and it connects the n-point joint probability distribution with an n-1 point joint probability distribution. Now, how do we go to the quantum description, or a possible way of going to the quantum description of a classical stochastic process? We define an operator x, and I will assume, and we imagine to perform certain measurements, and the outcome of the measurements will be giving me some certain probabilities, and so I will have certain random outcomes as a result of measurements performed on the given observable. And I define, for simplicity, just for simplifying things, I will consider the case of non-degenerate spectral decomposition of the operator x. So I will write this as sum over x of x phi x, and I will consider the case in which we only make projective measurements on the system. So I have for Neumann projective measurements. I will define with M the projective measurement operator, and I assume for now that M of x actually projective measurement giving the outcome x. And M of x applied to the density operator for the total system, because I can do this actually for a quantum system, not just for a classical system, will be given by, I have phi x, this is the probability of obtaining measurement x from this, okay, phi x, okay. And obviously, this will also have an evolution, a unitary, in this case, is a unitary evolution of the total system, the total system plus environment in this case. And I can indicate with U of T naught T, for example, the super operator which acting on T gives me the time evolution. So this is rho T of T naught, is thus U dagger of T, sorry, U of T, rho T of T naught, U dagger T. And this is the time evolution. And just indicate, for simplicity, the unitary, I introduce the super operator which describes the unitary dynamics for the total system. So I will have, in this case, what I'm considering is a sequence of evolutions of the total state, unitaries because it's the total state, then measurement according to a projective measurement operator, and then evolution again. Okay? And this will define me something which is the analog of this joint probability distribution. So I'm evolving at certain time interval, measuring, evolving, measuring, evolving, measuring, evolving, measuring. The outcome of the measurement is always some variable which is the analog of this xtn. And I have different time instants, obviously, because I'm dividing.
So Sabrina, in your quantum description, is this back to the total, which is the system plus the environment?
At the moment, I can do it on, I mean, the point I want to make is valid already at the level of the total system plus environment. You can also do it for the reduced system, but the fact that I cannot introduce a proper, my conclusion will be I will not be able to introduce a proper hierarchy of joint probabilities, or this is already valid for a closed system. It doesn't need to be an open system to reach this conclusion, actually. So for an open system, there is an extra issue which is related, well, I will not make it here, but my main point will be valid for the total system. It's really a quantum issue. If you want here the open open quantum system part is the presence of the measurements here. The fact that I don't have a unitary evolution, I have measurements. So what do I have here? I will have that I start from rho t. Okay. At time, I call it t naught. Then I have an evolution from t naught till t1. Okay. And then I have a measurement m, x, t1. Okay. Initial state, evolution, measurement. Then I will do the same again. Evolution from T1 to T2, measurement M, X, T2, and so on and so forth, until I reach the last part from Tn minus 1 to Tn, and measurement X, Tn. Okay. All this sequence will give me the quantum analog of the endpoint joint Tn x T probability distribution. Okay, so I have this joint probability distribution defined as for a certain process. And now here is the problem. The problem is here. It's precisely the fact that this object does not satisfy this consistency condition. And the reason is due to the fact, here I will have an mxtm u t1 tm, is due to the fact that when I make a measurement here, I may destroy coherences. Okay? I may cause the loss of interference effects. In quantum mechanics, we sum amplitudes, we don't sum probabilities. Okay? So the fact of the absence of a measurement at Tm, which is here, I can sum over all the possible measurement outcomes, everything is fine. Here may lead to something which is different, okay? Fundamentally different with respect to the presence of this measurement.
But if you sum up all x's in between,
it will still, of course, in some cases you can define situations in which this is true, but it will still not add up. I mean, the absence of measurement in quantum theory is not equivalent to a measurement where I don't know the outcome, okay? Because that would be just a presence of a measurement, but I don't know the outcome of the measurement. And still, the presence of a measurement where I don't know the outcome, it is still something which will change, which may change the presence of coherences. It can destroy any coherence, and therefore will influence the future dynamics. This is even to a further extent if I consider the system environment situation, in which, as a consequence of a measurement of the system only, the density operator of the environment, so generally this type of measurement uncorrelates system and environment, and as a consequence of this, I will have a collapse due to the measurement in the system part, and the state of the environment may depend in general on the outcome of the measurement on the system. So even there is a further difficulty if I consider the open system environment scenario, which is therefore highlighting the fact that the whole concept itself of a joint probability distribution, or also a conditional probability distribution, which would be the next step to define Markovianity in the classical case using Bayes' theorem, this cannot be extended straightforwardly to the quantum case. Okay? In general, there is no straightforward extension. And because of this, there have been a number of different descriptions or of possible extension or formalization of memory effects and non-Markovianity. There is not a unique way of defining what we mean with quantum non-Markovianity. My personal perspective is that all these different ways are useful. All these different ways are interesting for different problems or for different aspects of open quantum system theory. But there is no consensus of one way of describing non-Markovianity beyond, so outside of the classical case. In the quantum case, we can't just simply generalize. Yes?
I'm just confused about what the basic definition of non-Markovianity is. I would have said anything that involves more than a finite number of time derivatives in your GKSL by either that or modified by adding some more time derivatives.
You're talking about here?
Yeah.
Yes. Okay.
Anything that's not that is non-Markovian.
Yeah, this is what a lot of, let's say in our community, this was historically the definition of non-Markovianity. The reason is also that this came from the property of the dynamical map, which is associated to this form of master equation, which is the semigroup property. So the dynamical map, which is basically the solution of this master equation, satisfied semigroup property, and this corresponds precisely to this GKSL master equation. This is the most general form of a master equation, which is physical, so it gives a completely positive and trace-preserving dynamics for a semigroup. Okay. The point is.
Sorry. Next step could be that L also operator, this Lambda operator also function of time and depends on law.
Precisely.
And this would be,
precisely. You can let me. Yes, this is correct. Let me go one step in the direction of what you said. What I could do next is here I have this condition: LK must be non-negative. Now I could consider the case in which these are time dependent. Okay. If these are time dependent but still positive, okay, then obviously, or not obviously, well, you can prove that this, you can really use the Gorini-Kosakowski-Sudarshan-Limrad master equation. I mean, these are really trivial extension. The dynamical map is not a semigroup anymore, but it's divisible. So you have this divisibility property, which is, again, analog of this form of master equation. Therefore, many people also in our community believe that this is the proper way of defining Markovianity. It's a slight extension of what you said. It's the case in which positive or non-negative decay rates can be time dependent.
Operator dependent on time. Not only gamma, but L could be dependent on time.
Of course, also L can be time dependent, but you can write it in a basis in which it is not time. Sorry. Okay. I could stop here, but I agree with both of you. But the most important, I will conclude with this note, and then we can discuss. I guess there is time for questions.
So this is still Markovian.
This is what a huge part of the community would define in the case in which this becomes non-negative. So the case in which this form is violated. For example, the case in which there may be one channel for a certain time interval in which this becomes negative would be a not Markovian in the sense of divisible description. And for this, we don't have any guarantee, actually, that the solution is a physical solution, because we don't have this theorem anymore, and we are not sure that the dynamical map is completely positive anymore, because we don't have any theorem which guarantees complete positivity. But just to say that this was the state of the art some time ago. And then what people try to do here, and what I don't have time to do, but I will just end with this comment, is to use, instead of using mathematical definition of master equation, they wanted to have an idea of what it was the way of describing in physical terms memory effects. So they introduced the study of information exchange between system and environment, quantum information exchange between system and environment, and characterized the idea of memory effects as a return or a partial return of quantum information due to the presence of memory. And of course, this can be used in quantum technologies, and it is maybe I will mention only this. However, it has not been proven to be generally a resource for anything. So there is no resource theory of non-Markovianity. As far as I know, there are a number of counterexamples actually showing that in some cases, for example, for dynamical decoupling, some Markovian environments are better than non-Markovian environments in the sense that give a higher efficiency for dynamical decoupling strategies. But it's really
Sabrina,
a pleasure.
take a breath and thank
Yes.
More questions.
I think it was first.
Sorry?
It was first? I mean, you wanted to ask a question?
Yes, I had a question. So you talk about this Markovian, non-Markovian. This is very interesting, of course, but in practice, very often there's quite a simple answer in the following sense that in doing all of these things, you make a cut between the system to the environment, and this is where you put the Markov approximation. But very often, if you got certain degrees of freedom, that are strongly coupled, why not include them? And of course, the answer is if there's not too many degrees of freedom and your system doesn't become too large, then your world is still Markovian, and you don't have to pay the price of non-Markovian treatment. So
This is
the
true.
world is Markovian if you just make the cut right.
I would say that in a number, of course it is correct, in a number of scenarios, especially in quantum optics, in quantum optics everything is Markovian, but in a number of scenarios, you can actually do something which is called Markovian embedding. So you enlarge the Hilbert space of the system to include maybe one or more degrees of freedom. For example, in the case, imagine to have a two-level system interacting with an infinite bath of quantum harmonic oscillators. There might be one of the quantum harmonic oscillators, the modes of the electromagnetic field. There might be one of the modes of the electromagnetic field which is actually more strongly coupled to the two-level system. And therefore, if the dynamics of the two-level system even if the dynamics of the two-level system might be non-Markovian, if you enlarge your definition of system and include that mode which is connected or exchanging mostly energy with the environment, then the enlarged system will behave in a Markovian way, and clearly you can have a simpler description, which is the Markovian description. But, however, I must say, not always you can do it. So there are situations in which you can't do it, actually. And there are situations in which you have even classical noise that you can still describe with the formalism of quantum master equation, even if it's classical noise, in which you can't clearly think of a Markovian embedding. In many cases, I agree with you. It is the best strategy, but there are exceptions.
Okay.
Well, thank you very much for the excellent talk. I was wondering whether you could spend a few words on the implications of the theory of open quantum systems on the measurement problem.
Yeah.
Classical to quantum.
Yeah. Well, of course, in a simpler possible answer to this is the fact that generally the way in which we describe environment-induced decoherence is through a quantum master equation, in many cases a Markovian master equation, which allows to describe as a solution of this master equation the transition, for example, from an initial quantum superposition of macroscopically distinguishable state into the corresponding statistical mixture. So there have been experiments, for example, in trapped ion and cavity quantum electrodynamic scenarios, in which small superpositions of macroscopically distinguished shredding and cut-like states have been prepared. In the case of trapped ions, for example, the superpositions of a single ion moving right and left have been, so single ions confined in a harmonic potential, a superposition of different positions really of the ions in the harmonic potential have been created, and then the description of the transition from the quantum superposition of these, so to say, distinguishable, maybe not macroscopically distinguishable, but distinguishable states to the corresponding statistical mixture is provided by the solution of an equation of motion of this form. So it is not there is no complete satisfactory answer to the quantum measurement problem and to the quantum to classical transition, but it is the framework which allows to describe, at least when it comes to environment-induced decoherence and objectification, quantum Darwinism, a number of other ways of describing the emergence of an objective and of the objective reality somehow, and so the loss of the quantumness in terms of the superposition, you use this framework to model this transition. This is at least one of the possible answers.
Thank you.
Okay.